Okay, so let's talk about the tire modeling. The modeling of the ground tire interaction that obviously is taking place in this model, all right? And so it's actually a very rich topic. Loads and loads of research has been done on it over the years, and you'll hear names like the Pacheco tire model, the Magic Formula tire model, but there's a lot there, all right? And in general, these very elaborate models, they kind of work on kind of, I'll call it a structural deformation kind of approach. And they think of the tire ground interface as what they call the patch, which maybe you can see it right here in yellow. And from that, they get essentially a mathematical model that's based on understanding the forces and moments between tire and ground. And once you know those forces and moments, they just kind of propagate through the entire mechanical model, which in our case will be the full forklift. All right. And so we're going to go a little bit simpler than that. And that's what was done in this forklift model. And you might justify it because the tires are pretty hard on a forklift, and the surface is hard, and the surface is very flat. But think of what they're doing here as kind of a general 6-dimensional model that includes the 3 XYZ forces as well as the 3 XYZ moments. What we're going to do is basically get rid of the moments, all right? And to do that, what you really do is you model the tires as spheres, all right? And it seems very like, oh, wow, you got that whole big spherical surface. Well, what we really only care about is one point, especially one point when we're driving on a flat surface. And that's this point at the lowest point of the sphere where it comes into contact with the ground, all right? So anyways, with that idea in mind, I want to kind of show this model to you. So let's get it centered a little bit. And maybe it's easier to look at it with the spheres kind of hidden. But think of the spheres as rigidly connected to those gray discs, all right? And therefore, as the tires rotate, the orange spheres will too. And the part of why I wanted to do this was I really wanted to make sure I got the steering into this too. And so you'll see that I put in a little rack and pinion steering like that, right? And I set it up with an actuator, so as we bring it into Simulink, we'll be able to control the steering angle. So anyways, let's bring this into Simulink. We go to motion results, and we will export to Simwise XML. Okay, so here we are in MATLAB, and there's our XML file, what I call our blocky car with steering. And so let's create the Simulink model. And again, all we do is double click on that XML file to launch the process of creating the Simulink model and project. Here comes Simulink model, and it populates it with all the appropriate blocks and parameters. And we hit the run button, and there's our vehicle. All right, so let's get those tires turning. And so we'll prescribe the motion. So we'll configure it as a motion configuration, which is now looking for commands for each of the rear wheels are going to propel it, and then the rack and pinion. For the rear wheels, and then with one source of motion. And I did some practice, so I kind of know to get it to move forward, I need to make it go in a -5. And this is all kind of references, so it's not really that big of a deal. But anyways, let's go from 0 to a magnitude of 5 meters, or 5 rotations, 5 radians per second. Let's do that in a 2-second period. Okay, so we see the 2 rear tires turning. Now, to do the steering, I'm going to do something called a ramp sinusoid, right? Right, and so this is going to basically move that little rack back and forth about 15 centimeters. So the amplitude will be 0.15. The period of oscillation, think of like, what do they call it, like a serpentine kind of test for our steering. We'll make that 5 seconds. And this, I think, will make sense perhaps when you see it. But anyways, I'll keep that at 2. Okay. So we see the steering is started and the back tires are spinning. So let's have a drive on something. Okay. And for right now, I think I'll put the surface in first, and then we'll kind of establish the, I'll call it the contact wall between the tires and the surface. So under Simscape multi-body surfaces, we'll choose an infinite plane. This, well, we'll kind of get to this in a second, but I'll show that, well, let's just kind of save that. We'll be there in probably like a minute or so. But we need to tell it where it is, this infinite plane. I'm going to put it right at the origin, which is initiated in there. And then I'm going to make the plane, let's make it 10 meters by 10 meters. And we'll see that we'll offset it too, but there's our plane. And the car is kind of embedded in it. So we're going to lower it, and we'll just use a frame transform to do it. And we'll make it minus 0.3 meters lower. And we'll just kind of check our positioning right now. That looks pretty good. Okay. So let's look at the model. Clean it up just a little bit. I'll drag that down like there. Let's drag that down. And maybe get a few of these diagonal lines straightened out. And perhaps I'll do a little bit more later. But for right now, I can kind of see, and I kind of knew these spheres are going to be kind of at the end of each of these threads. And so let's go in here. All right. And that the process of really kind of establishing the connection, it's really about surfaces and then I'll call it a force law. All right. And so for these spheres, it's really not bad. It's all kind of embedded into how Simscape multi-body works. And it's essentially this idea of exporting the geometry, right? Make it a little smaller, move that up like there. And that we'll use one of these external ports to kind of connect into it. And here's why I'm able to really kind of say this port's a little bit different, where this is about Cartesian coordinate systems, usually local ones, that we use for connection and tracking things in 3 dimensions. You know, they're Cartesian X, Y, Z. This is really about surface, right? And so, anyways, I'll call this, what do I want to call it? I'll just call it contact surface. And let's put this on the right side. And I'm going to copy it because we're going to use it in the other 3. All right, so that's what we just did. So we're going to do it for the other 3. So in finishing up the 4th one, I'm getting pretty good at this now. Export, paste in the port. All right, and so we got all 4 of them done now. All right. And so now we're going to get the contact force set up. And this is what they call kind of like a smooth spring damper force law. And think of it really as the spring is really the compression of the tire. And to kind of keep the math simple, and also keeping in mind that we can kind of tune these parameters, we can get pretty accurate for our means. And it's really the force law is really about that normal force between tire and ground being expressed, and characterized by these parameters. And then there is, of course, a static friction, dynamic friction law in place for kind of the side loads. So it's pretty, I'd say, traditional, right? And pretty easy to put in. And so we just kind of use those defaults for all 4 tires. Yeah, and the topology, I'll call it, for all this is about 4 tires connected with the same surface, right? And we already created that surface, and we need to kind of get out to it still. There you go. And so let's hit space, drag one of these guys over here. Let's Control I. Yeah, that's that hexagonal SimScape external port. And let's hit space so I can see the whole. We'll name this ground surface. And we want that to be on the right side. So let's go back in here and make that a right. All right, that's pretty easy. And so we'll just kind of connect that in. All right, and we'll hit run. There's one more thing to do. So it's going to kind of reveal that quickly. Okay, still not moving. And that's because our connection to the world taking place through that port right there. That's what that is a well joint still. So we'll replace that with a 6-stop joint, which really isn't a joint at all, but it really does kind of, I'll say it provides the freedom for the full vehicle to kind of move freely in the 3-dimensional space. So with that, we'll hit run. And just like we saw in the previous video, that contact's I'll call it a little bit tougher kind of thing to model, and there are solvers that are real good at it, and so let's make that choice here. And you might recall that it was the DAE SSC, so DAE for SimScape solver. It does this quite well. There it goes, with pretty good steering. And from our forklift model, we can see those embedded spheres. There's one. And there are the others. And we can get to the location of the model right here. And there you see the connection to the surface. And there's the fixation or the connection of the spheres into the tires. Thanks for watching.